Hello, in this video I'm going to look at numerical integration using the midpoint rule. So numerical integration is essentially bypassing the part of which that you might have learned in, say for example, like Calculus 1, where you have that the integral, like let's say like from a to b of f of x dx, that basically it's equal to some antiderivative, which we can call big F of x, from a to b, of which then from there we just simply evaluate f of b minus f of a. Well, in any case, that works if, for example, that we know the antiderivative. But let's say that we want to do this via numerical approximations. Well, we can actually do that. How do we do that? Well, the main thing that you would need to do is you would have to consider that your function f is continuous. So you have to have that f is continuous on the closed interval from a to b. Now from there, you would probably need to say that, for example, we'll create some delta x, which is basically just b minus a over n, where n is just a positive integer. So from there, we need to consider the partition. So the partition is, well, you're going to have a equals to x0 plus, not plus, but comma, x1, and then furthermore, you'll have that the xn will be equal to b. Now, in any case, that assumes that essentially that a is less than b, for example. So from there, we need to basically consider that the midpoint will be given by, okay, so the midpoint sum is given by the series sum from I equals to 1 to n, and we're going to take f of mi and multiply that by delta x. Now, in any case, the mi is actually just the midpoint of the it's the midpoint of the ith interval, of which we'll just put like a little formula right there. Now, what do we mean by that? Well, notice that, for instance, that over here we have a bunch of intervals, right? And for each of those intervals, we're just taking right down the middle in either case. So in either case, the point mi, it lives inside the bounded interval xi minus 1 comma xi. Now, in order to kind of understand this though, it's probably just best to look at a simple example. So for example, we have that what if we were integrating, let's say 2x plus 1, and this is dx, and we're going to say that this is from 0. Okay, so we have that this is from 0 to, let's say, 1. Now, in any case, what if, for example, that we use that n is equal to 2? Well, what that would mean is that delta x would be 1 minus 0 divided by 2, which would be 1/2. Furthermore, this would tell you that your partition of your interval would be 0, 1/2, and then you would just have 1. Okay, so from there, we just need to find the subintervals, which we have 0, comma 1/2, and then we have 1/2, comma 1. Now, all that this means is that basically we just need to find the first midpoint, which in this case would be the midpoint of 0 and 1/2, which that's going to be 0 plus 1/2, but accordingly divided by 2, which is just 1/4. Furthermore, we can find the second one by taking the midpoint between 1/2 and 1. But another way that you can do that easily is by saying that your delta x is going to determine the next one, which means that you just need to increase from 1/4 to another 2/4, which will give you 3/4. That's no different from just saying 1/2 plus 1 is 3/2, but divided by 2, you get 3/4 still. So in this case, I calculate it kind of like two ways, essentially. Now, from there, we say that the midpoint sum is given by delta x, which is essentially just going to be 1/2, but you're going to multiply that by the function values that we need to find, which in this case would be 1/4 plus f of 3/4. Okay, but that's going to be 1/2 times 2 times 1/4 plus 1 plus 2 times 3/4 plus 1. Now notice that, for example, that each of these is going to reduce nicely to, let's say, 1/2, and then you have plus 1 plus 3/2, and then you have plus 1. Now, it looks that, for example, that you have that the midpoint sum with two subintervals is going to give you, let's see, well, you have 3/2 plus 1/2 is 4/2, which is actually just 2. So you have 1/2, 2 plus another 2. But notice that this is going to be 4 divided by 2, which is in fact equal to 2. So we find that basically that the midpoint sum using two subintervals for 2x plus 1, it's equal to 2. Now, take into consideration that if you would have probably integrated from 0 to 1 of 2x squared, not 2x squared, it's 2x plus 1, that this would have given you the following. It would have given you x squared plus x from 0 to 1, of which in any case it gives you 2. Now we see that the midpoint sum for this particular function is actually very accurate in that sense, of which that's not any surprise really. But let's say that we want to try, a different function perhaps. Okay. So let's say that we have the following function, the integral from 0 to 3 of 9 minus x squared dx, and let's say that we use that n is equal to 3. Okay, so we're just going to increase it by 1. Delta x is equal to basically 3 minus 0 divided by 3, which is equal to 1. So that means that our partition is going to be 0, 1, 2, and 3. Okay, well that means that basically we can find the midpoints. So the first one would be 1/2. The second one would be, well, basically 3/2, because we know that we're just adding 2. And then the third one will be 5/2. And then accordingly, that's actually it. Why? Because remember that you're only creating 3 subintervals. So you have 0 to 1, 1 to 2, and then you have the last one being from 2 to 3. So we have 3 subintervals, 3 points, and so on. Okay. Now, the rest is that we just need to substitute this into our equation. So accordingly, we have that the sum m3 is equal to 1 times, okay, so now we're going to say 9 minus 1/2 squared plus 9 minus 1, not 1, but what is this? This is 3/2 squared plus, okay, so now we have 9 minus 5/2 squared. Okay, now notice that basically 9 plus 9 plus 9 is 27. So we have 27 minus 1/4 minus 9/4 minus 25 over 4. Now, in either case, we could probably say that, for example, that this is going to give you 27 minus 35 over 4. Okay, but now we can actually just go ahead and say, well, let's take the common denominator and say 4 times 27, which is going to be 108 divided by 4 minus 35 over 4. And basically, this is going to give you 73 over 4. Now, of course, we can get that approximation if we need to, of which, in any case, 73 divided by 4 is 18.25. So we have that's going to be 18.25. But that's units squared, by the way. Now, what if we were to basically find, for example, the real area for 9 minus x squared? Then in that case, if you integrate from 0 to 3 of 9 minus x squared dx, well, it's going to give you 9x minus 1/3 x cubed from 0 to 3, of which in any case that's going to be 27 minus, okay, so 27 divided by 3 is 9, which means that it's going to be 18. Okay, so we see that basically we're off by 0.25 squared units, and that's actually okay in terms of like finding the midpoint in either case. Now, if we want to, we can actually estimate, for example, the error that we can have. For example, I have that the error for the midpoint is given by the maximum that I'll call m times b minus a cubed divided by 24 n squared. This is the error bound. But what is m? M is basically just the maximum at which you have your second derivative. So it's going to be just the max, but it's going to be the max specifically at either B or A, depending. So, we can actually determine, how much we need to calculate the midpoint sum if you want it to be within close proximity. If you were going to, let's say, for example, integrate from 0 to 1 of e to the x squared minus some midpoint sum and set the bound to be no bigger than 0.01, then basically by using this error formula, you're going to find that the error is going to tell you that n has to equal 9 in order for the error to be no bigger than 0.01, because we can't find a conventional method of integrating e to the x squared. So in that sense, we just go ahead and we avoid it by taking the numerical approximation for the the integral from 0 to 1 of e to the x squared. Okay, so in any case, we can actually try an example such as, like if we want to try to see how many derivatives do we need to take in order to be accurate. But, let's say that you're integrating from 3 to 5. Well, let's say 3 to 8. And then you have 5 over x squared, and then you have dx. So let's say that, for example, that you wanted to find a midpoint sum that is no bigger than 0.01. So try to see if you can find, for example, the first derivative, second derivative, and then go ahead and plug in 8 or 3 and look for the maximum to see like what size would the midpoint sum have to be in order to find that the error is no bigger than 0.01. Okay, so in either case, you can also determine, for example, like what's the real value, because remember that you can find for some of these, you can actually find what the real value actually is by using your conventional methods of integration. But remember that you may not actually be able to do that because then it may not be possible to integrate something or to take the antiderivative of something. So here we have that this would be 3 and that would be an 8, and then you get negative 5/8, and then you get plus 5/3. But then from here, you take that using a common denominator, you will have that this would be 40 minus 15, which is 25 over 24. So in this case, this is the real answer. But again, what we want to do is try to figure out what size n would have to be so that we're at least close by 2 decimal places or something like that. Okay.